Hi guys, we're going to talk about VSEPR theory today. So VSEPR, that stands for Valence Shell Electron Pair Repulsion Theory. So let's try to think of what that means. So valence shell, that means the outermost energy level, the highest energy level. Electrons, so the valence electrons, or the electrons that are in the highest energy level. Pair, so those valence electrons exist in pairs, in twos. And repulsion, they repel each other. So the valence electrons exist in pairs and they repel each other. So based on this, we know that because electrons repel each other, the molecules are going to adjust their shape so that those valence electron pairs are as far away from each other as possible. So let's write that down. So molecules adjust their shape so that valence electron pairs are as far away from each other as possible. And so because of that, that determines the geometry and the shape of the molecule and the bond angles and all that. So that's what we're going to look at today. So we're going to start with SiH4 as our first example. And for these, you got at the beginning of the year an activity bag. So I want you to find in it a little baggie that has some marshmallows and some toothpicks. So pause the video for a minute until you find this bag and bring it so that you're using it while you're taking your notes. So we're going to draw SiH4 first. So silicon has 4 valence electrons and it's going to bond to 4 hydrogens. So it's going to look like this. Okay, so once you make it, what you do is you look at your central atom. That means the atom that's in the middle. And you see how many areas of electrons are around. So it looks like there's an area of electrons, there's an area of electrons, there's another one, and there's another one. So 4 areas of electrons. So these electron pairs or electron areas repel each other. And so they're going to stay as far away from each other as possible. So what I want you to do is in your baggie, you're going to take the big marshmallow. That's going to be your central atom. And then the little ones are going to be your peripheral atoms. So this is going to be your silicon in this case, the big one. And the little ones are going to be your hydrogens. And the toothpicks are going to be your bonds. So you're going to stick the hydrogens onto the silicon. You want to do 4 of these. And you want them to be as far away from each other as possible. So again, pause the video. Try to make it into a shape that would make these 4 bonds as far away from each other as possible. So some of you might have gotten to look like this, where they are 90 degrees from each other. And some of you maybe got it to look like this. So which one do you think is the real shape? On paper, we draw it like that because paper is 2D. But in reality, molecules are 3D. So they are going to try to spread as far away from each other as possible for the electrons to be as far away from each other as possible. So this would be the better shape. If you look at the bond angles here, they're about 90 degrees. If you look at the bond angles here, they're a little bit bigger than 90. Again, because it's a 3D molecule, so it's going to spread out a little bit more in 3D space. So this is the shape of that molecule, where you have 4 things as far away from each other as possible. That bond angle, so the angle between 2 bonds, is 109.5 degrees, and that's a number that you need to know. 109.5 degrees. Let's look at the shape of the electrons and the shape of the molecule. And in this case, they're both going to be the same. So we have a central atom right here. So that's going to be my central atom. And then I have one going up and then I have 3 that are on the bottom, kind of making a tripod shape. You do not need to draw it. I'm just drawing it for my notes so I can remember what it looks like. On the test, you do not need to draw it. You just need the name of the shape. So this shape is called a tetrahedral. So I'm going to write electron geometry as EG and molecular shape as MS. Both of them are tetrahedral. Now, the electron geometry is the shape of the electron areas. So the shape that the electron areas are making. The molecular shape is the shape that the bonds are making. And so when you have all your electron areas in bonds, then the electron shape and the molecular shape are going to be the same. That's why here they're all the same. If you have lone pairs, then your molecular shape and your electron geometry will be different. But in this case, they're both the same. So this is called a tetrahedral because tetra means 4. Have you ever played Tetris? They always have like blocks of 4. And so this is called a tetrahedral because it has 4 sides to it. So there's 1 side, 2, 3, and 4. So tetrahedral. And it's symmetric from all angles. Here's another one. There's another tetrahedral, just a bigger one. Okay, the hybrid for this one. For the hybrid, you look at how many areas of electrons are around your central atom, and there are 4 of them. And so you need 4 orbitals to mix together in S, and then 3 p's, so sp3. Let's look at the next one, pH 3. So we're going to draw that first. We're going to draw the lowest dot structure. So phosphorus has 5 valence electrons. It's going to use 3 of them to bond to the 3 hydrogens. And then it has an extra lone pair here. So once you draw it, you count up how many areas of electrons are around your central atom. And you want those to be as far away from each other as possible. So in your shape that you made, hopefully you made the tetrahedral. If not, then go ahead and make the tetrahedral with the 4 different bonds that we had for the SiH4. So like this, there's your tetrahedral. And now there are 4 areas of electrons, so the bond angles are going to be the same, right? Whether they are in bonds or whether they're in lone pairs, they're still electrons. They're still going to repel each other. So we still have 4 areas of electrons. So make 4, just like we did with SiH4, but then take out one of your marshmallows. Take out that hydrogen. Or there you go. We're going to keep the stick there to show us that there's still some electrons here, but those electrons are in a lone pair. So it looks like this, right? So the bond angle is still the same because there's still 4 areas of electrons. So 109.5 degrees. Now let's look at this shape. So we have a central atom. And then we have these 3 on the bottom that make the shape of the tripod. But now we have a lone pair here instead of a bond. Here's my tetrahedral. If I were to move one of these, but keep the angles the same, it would look like this. So again, central atom, 3 bonds, making like a tripod shape, and then there's a lone pair there. And so again, the angle is still the same because I still have 4 areas of electrons, and they're still repelling each other. Whether they're in a lone pair or bonds, they're still going to repel each other. So let's look at this shape. So the shape that the electrons make is still the same because there's still 4 areas of electrons. So the shape of the electrons is still a tetrahedral. But what is the shape of the molecule now? The shape of the molecule is a little different because not all the electrons are in bonds. And so this shape is called Trigonal Pyramidal. Let's write that down and then talk about why it's called that. Trigonal Pyramidal. So the reason why it's called trigonal pyramidal is because it looks like a pyramid, right? Do you see the pyramid? And it's a base 3. It's pyramid base 3. Normal pyramids are like a square on the bottom. This one is like a triangle on the bottom. So it's trigonal pyramidal is what it's called. The hybrid, 4 areas of electrons, so still sp3. So when you do these, what you want to do is draw your Lewis dot structure. Once you have the Lewis dot structure, count up how many areas of electrons are around. That's going to automatically tell you the angle. It's also going to tell you the hybrid. So if it's 4 areas of electrons, it's always going to be 109.5. It's always going to be sp3. And the electron geometry will always be tetrahedral. The molecular shape is the tricky one, where, you know, it could be different things depending on if they're all in bonds or if not. Okay, SH2 is the next one. So sulfur has 6 valence electrons. 2 of them are going to be bonded to the hydrogens, and then we have 4 that are in lone pairs. So it looks like this. So again, you count how many areas of electrons are around your sulfur. 4. That automatically tells you the angle is 109.5 degrees. It automatically tells you it's sp3 hybrid. It automatically tells you the electron geometry, the shape of the electrons, is a tetrahedral. But now let's look at the shape of the molecule itself. So here's the tetrahedral, the original tetrahedral, if they were all in bonds. We took one out, and we got this. Take another one out, and then what do you see? It should look like this. So I still have 4 areas of electrons, but 2 of them are in lone pairs and 2 of them are in bonds. So it looks like this. So I'm going to draw a picture for myself just to remind myself what it looks like. It looks like there's your central atom. There are 2 things sticking out at 109.5 degrees from each other, and then I have 2 lone pairs here. This shape is called bent or angular because it looks like an angle, or it looks like a bent line. So molecular shape, we're just going to call it bent. By the way, we're going to worry about polarity and IMF a little bit later, so don't worry about it for now. We're just going to fill up to the hybrid box. Okay, BeI2. So let's look at BeI2. Beryllium has only 2 valence electrons, and it has to bond to 2 iodines. So it has to bond to this iodine and this iodine. We've used up all the valence electrons from the beryllium. Each iodine has 7. 1 of them is in the bond, and then you have 6 more in lone pairs. So it looks like this. All right, so I want you with your marshmallows to now take off all the extras, and so you should have just 2 of these that you're going to stick on, and you want them to be as far away from each other as possible, and see what shape you got. So pause, try to figure it out. And if you're trying to get 2 things to be as far away from each other as possible, you should get this. Should look like this. So what angle is this? What is the angle between this bond and this bond? What's this angle? That is 180 degrees. So let's try to draw a picture of this. We have my central atom, and then I have 2 things sticking out at 180. Oops. You know, I can't draw right. There we go. So all my electron areas are in bonds, so my electron geometry and my molecular shape are going to be the same here. And what do you think this is called? It's called linear because it looks like a line. It's an easy name. So my electron geometry and my molecular shape are both linear. Let's look at the hybrid. So you look to see how many areas of electrons are around your central atom. There are 2, and so 2 would be 2 orbitals mixing together, S and P, so it is an sp hybrid. BCl3. So boron has 3 valence electrons. It has to bond to 3 chlorines. 2, 3. So we've used up all its valence electrons. Each chlorine has 7. So 1 is in the bond, and then the other 6 are in lone pairs. So each of these chlorines have 3 lone pairs. So it looks like this. So you count how many areas of electrons are around your central atom. It looks like there are 3 areas of electrons. Here's an area, and here's an area. So again, with your marshmallows, stop the video and try to put 3 things as far away from each other as possible. And this is what you should get. 3 things as far away from each other as possible. Look like a peace sign or a Mercedes logo. And so let's look at this bond angle. What do you think? What is this angle? So it's 120 degrees. Okay, let's try to draw the shape for our notes. So central atom in the middle. And then you have 3 things coming out at 120. Because we don't have any lone pairs, because all my electrons are in bonds, the shape that the electrons make and the shape that the bonds make should be the same. And both of them are called trigonal planar. Trigonal planar. Why is it called trigonal planar? It's called trigonal because it looks like base 3 triangle, right? And it's planar because it's in one plane. It's like almost a 2D shape. So because it's in one plane, it's planar. Now compare this to trigonal pyramidal. If you remember, this was my trigonal pyramidal right here. This is my trigonal planar right here. What's the difference between them? They're both base 3, but the angle is different. This one's trigonal pyramidal because it looks like a pyramid. It's pushed down like a pyramid. This one's trigonal planar because it's in the plane. The reason is because there are 4 areas of electrons here because of that lone pair. 4 areas of electrons, so the bond angles are 109.5, and so it looks like a pyramid because those bonds are pushed in. This one only has 3 areas of electrons, so they can spread out more, and the angle is 120. So trigonal planar, trigonal pyramidal. Okay, the hybrid, 3 areas of electrons, so that means 3 things mixed together, 3 orbitals mixed together in S and 2 P's, so sp2. Okay, GeBr2. Germanium has 4 valence electrons, and it has to bond to 2 bromines. So there's my germanium. It's going to bond to a bromine, and then it's going to have a lone pair left over because it has 4 valence electrons. Bromine, each of them have 7, so one of them is in the bond, and then you have 6 that are in lone pairs. So it looks like this. First thing you do, count how many areas of electrons there are. There are 3 areas of electrons. That tells you the angle is 120, because 3 things can be as far away from each other as 120. It tells you the hybrid is sp2. 3 orbitals need to mix. It also tells you the electron geometry is going to be trigonal planar. So as soon as you draw your Lewis dot structure, count how many areas. It tells you the angle, it tells you the hybrid, it tells you the electron geometry. Then the molecular geometry is what you try to figure out. So we have our trigonal planar here with the 3 areas of electrons. We're going to take 1 away. And so it's going to look like this. So still 3 areas of electrons, but one of them is in a lone pair, and the other 2 are in bonds. Let's draw a picture of this. Here's my central atom, 2 things coming out at 120, the lone pair there. What shape does that look like? That looks like a bent, right? Remember, like the one on top here? It's the same shape as the bent, as this one right here, right? Same shape. Now let me show you both of them. we can compare between them. Here they are. They both look the same, right? What's the difference? The only difference is the bond angle, right? This has 3 areas of electrons, so the bond angle is 120. This one has 4 areas of electrons. It has 2 lone pairs there, so the bond angle is 109.5. So this one's a little bit smaller angle than that one, but otherwise the shape looks similar. Why is the bond angle different? Because of the areas of electrons. This is 4 areas, so 109.5. This is only 3 areas, so they can spread out more to 120. They're both a bend shape. Now you'll notice some of those 3 last ones that we did, they don't really obey the octet rule. The central atom doesn't have 8 valence electrons, but there's nothing else we can do. We can't really bond anymore because they run out of electrons. Okay, ASF5. Arsenic has 5 valence electrons, and it has to bond to 5 different fluorines. So it's going to use each of its electrons to bond to a fluorine. 1, 2, 3, 4, 5. And each fluorine has 7 valence electrons, so one of them is used for the bond, and then each of them has 6 electrons that are in lone pairs, which means 3 lone pairs on each. It's a lot of lone pairs there. Okay, so this one's kind of the opposite of what we just talked about. This arsenic has 10 electrons on it. It's more than the octet. And so that's kind of the opposite. We call that an expanded octet. But there's no way that arsenic can bond to 5 fluorines without having 10 electrons. And so you'll know because there's no other way to draw these. So you count up how many areas of electrons are around your central atom. There's 5. So I want you now to take your marshmallow, stop the video, try to put 5 of these on there and spread them as far away from each other as possible. And then come back. If you put 5 things as far away from each other as possible, this is what you should get. So if you don't have this, go ahead and make it on your marshmallow so you can see what the shape looks like in front of you. So take your marshmallow, put 1 up, 1 down, so that you make a line. And then on the opposite plane, make them 120 degrees apart, so it looks like a peace sign. So 1 up, 1 down, and then the other 3 are 120 apart. That's the shape. Let's look at the angles. So this angle is 90, right? All these angles are 90. So 90 degrees. But then these are 120 apart. So this shape actually has 2 bond angles, 90 and 120. Let's try to draw what this shape looks like. So I have a central atom, 1 up, 1 down, and then the other 3 kind of 120 apart. The shape of this, the electron geometry and the molecular shape are going to be the same because all your areas of electrons are in bonds, and both of them are called Trigonal Bipyramidal. Trigonal Bipyramidal. Trigonal Bipyramidal. Let's talk about why it's called that. It's kind of a complicated name. So remember the trigonal pyramidal we had? This was trigonal pyramidal versus that one's trigonal bipyramidal. It was called trigonal pyramidal because it makes the shape of a pyramid and it's base 3. Right, so now let's look at the shape we're looking at, the trigonal bipyramidal. Ignore the bottom part. Do you see the pyramid on top right here? It makes the shape of a pyramid. So that's a pyramid. Ignore the top part. Do you see the bottom pyramid, upside down pyramid on the bottom? So there are 2 pyramids here. One upside down right here and one on top. And both of the pyramids are base 3. So trigonal pyramidal, but there's 2 pyramids, so trigonal bipyramidal, 2 pyramids that are base 3. I know the names are a little strange, but they all have a reason. They all should make sense. The hybrid, let's talk about the hybrid. So we have 5 areas of electrons that need to mix together. And so S, 3 Ps, and then a D, sp3d. So we said that this is an expanded octet. It has more than 8, right? So the reason why we want 8 is because we have one S and 3 Ps, right? Each of these 4 orbitals take 2 electrons, so a total of 8. So when we fill our S and P sublevels, we have 8 electrons. Well, guess what? The extra 2 electrons, because we said this has 10 on it, the extra 2 electrons go into a d orbital because the d orbital is available for it, and it's empty, so now we put 2 electrons in there. Okay, SF6 is next. Sulfur has 6 valence electrons, and it's going to bond to 6 fluorines. So it's going to use each of its electrons to bond to a fluorine, and that takes care of all its valence electrons. And then each fluorine should have 3 lone pairs on it. Okay, we count up how many areas of electrons are around. There are 6 areas of electrons. So now I want you to pause the video, back to your marshmallows, put 6 things as far away from each other as possible. And you should get this shape. So 1 up, 1 down, and then the other 4 make a plus sign. 1 up, 1 down, the other 4 make a plus sign. Okay, make sure that you're making these with your marshmallows so that you can have a visual in front of you. So let's look at the bond angles. All the bond angles here are 90 degrees, no matter where you look. They are all 90 degrees. This shape, we have a central atom, 1 up, 1 down, and then the other 4 make like a plus sign. This shape, both the electron and molecular geometry should be the same because all the electrons are in bonds, is called octahedral. And the octahedral means 8 sides. So there's 1, 2, 3, 4, and then on the bottom 5, 6, 7, 8. So octahedral. The hybrid, we have 6 orbitals that need to mix. So an S, 3 Ps, and then 2 Ds. So sp3d2. Oops. No. I don't know why this is. Can't write. There we go. Okay, these are all the shapes that you need to know about. The other 2 on the bottom here are just extra practice. So let's do them just for extra practice, just practice what you would do. So HCN, so carbon has 4 valence electrons. 1, 2, 3, 4. Hydrogen has 1, nitrogen has 5. 1, 2, 3, 4, 5. Let's bond everything once. There's 1. There's 1 bond. Hydrogen's good with its duet. Carbon right now has 6. Nitrogen also has 6. So bond another pair. Now carbon and nitrogen has 7 each, so bond a 3rd pair. And so now they're good. But we're going to write it so that it looks a little bit neater. And then the nitrogen here has a lone pair. So now you look at your central atom. There are 2 areas of electrons. That tells us the angle is going to be 180. That's the farthest 2 things can be apart. It also tells us the hybrid is sp. And it also tells us the electron geometry is going to be linear because you have 2 things that are 180 apart. My molecular shape is also going to be linear, since you have all your electrons in bonds. And so it's going to look like my linear shape right here. It doesn't matter that one of them is a single bond and the other one is a triple bond, it's still linear. Last one we'll do is C2H4. So I'm going to do it down here. There's carbon with its 4. There's the other carbon with 4. We have 4 hydrogens. There's 1, there's 2, 3, and 4. Bond everything once. And now hydrogens are good with their duets. Carbon, each of them have 7, so make a double bond, and now everybody's good. So just redraw it so it looks a little neater. So it looks like this. You look at your central atom now, it looks like, you know, both of these carbons are in the middle, so pick one. It doesn't matter which one. So let's pick this as our central atom and count how many areas of electrons are around. So there's 1, 2, 3 areas of electrons. That tells us the angle. 3 things as far away from each other as possible are 120. The shape looks like this, and both the electron geometry and the molecular shape are trigonal planar. And the hybrid would be sp2, since there are 3 orbitals that mix together.